Today we're starting our unit on outer space, and we're going to have our little introduction to gravity today, and then I'll tell you about the rest later. So every physical object, so including all matter, right? Gases, liquid, solid, whatever. All physical object, all matter, right, has mass. Okay, has mass. So every object or anything with mass has its own gravitational field. Okay, its own gravitational field. So that means you, yes, you exert gravitational force on everything around you. Okay, so the gravity that holds you to the earth has two components. Okay, the force Earth exerts on you and the force you exert on the earth. However, we calculate this combined force with the force between two objects with one calculation involving two masses. Okay, two masses. So we're going to take a look at that today. So we measure the force between two objects, the gravitational force. So we measure the gravitational force between two objects with a formula. F equals G, big G, times M1 times M2 over R squared. Okay, and so let me, good. Okay, and let me look at G M1 M2 over R squared. Yeah, okay. And so what in the world are all of these things? In fact, let me put this formula in the middle of the page so that we can sort of diagram it a little bit better. Equals G times M1 times M2 all over R squared. Okay, so this is the universal gravitational constant. Okay, and it's we're going to call it 6.7 times 10 to the negative 11th. And it's Newton meters squared per kilogram squared. Okay, Newton meters squared per kilogram squared. And this is this guy over here, and I'll use red to point to this guy. This is mass of object 1. Okay, it's in kilograms. And then this guy over here, right, is mass of object 2. Also in kilograms. Okay, and then this guy over here is, this whole term is the square. Actually, I'll just define r because we know we're squaring it. So r is the distance between the two objects. Okay, and that's in meters, and it's really properly the distance between their two centers of mass. Okay, the distance between their two centers of mass, but in most cases this approximation is going to be just fine. Okay, and for our purposes I think it will be. Okay, so the distance between the two objects, okay, in meters. All right, so go ahead and take about another minute to copy this down, and then we'll do an example. I'll point out, right, this gravitational constant is going to give us force. So F is the force, right? So F is, this is force, okay, in newtons, right? And how do we get to newtons? Well, if you look on top, you've got, on top of this equation, you've got meters squared here. And then on the bottom, you're going to have r squared. So that's going to be in meters squared. Meters squared will cancel out. You've got kilograms squared on the bottom of g. Then you're going to have kilograms squared on the top over here. Kilograms squared will cancel out. So all you're left with is your final unit is in newtons. Okay, so that's how the unit cancellation works here. We're not going to spend a lot of time, I think, worrying about the unit cancellation. I'm just going to show it to you right now, and we're gonna sort of ignore it as we move forward, and we're just going to understand that as long as our masses are in kilograms and our distance is in meters, we'll get newtons as our force. Okay, and we'll move forward. But I wanted to show you the cancellation there. So here's a question worth asking. What is the force of gravity between the Earth and the Moon, right? How would we calculate this? Well, we know that F, and I'll kind of put this in the middle again, F equals G, M1, M2 over R squared. Okay. We start with universal gravitational constant, which is 6.7 times 10 to the negative 11th Newton meters squared per kilogram squared. And we're going to multiply this by the first mass, which is the mass of the Earth. So really it's about 6. So, well, let's go 6.0. We're going to round to 1 decimal place. 6.0 times 10 to the 24th kilograms. That's the mass of the Earth. Times mass of the Moon. Mass of the Moon is 7.3 times 10 to the 22nd kilograms. Okay. All divided by the square of the distance between them. So it turns out that it's 3.8 times 10 to the 8th meters. And then this whole thing needs to get squared. Okay, so that's going to be fun. I'm going to actually do that one on my calculator, but I'll double check it with just normal math. Give me a tick. If we can get a mental math approximation for this, and let's see what our calculator says. So let's just knock this out. So 6.7, you won't mind if I round that to about 7. And then, so let's multiply these constants first. And then 6, that's about like, well, that's 6. So 6 times 7 is 42. Now, because we got 6.7 instead, let's just call that 40. So let's call that product 40. Now we're going to multiply by 7.3. You won't mind if I round that down to 7. So 7 times 40, that's going to be about 280. Okay, so we're just handling the constants first, right? 280. And then 3.8 squared, let's call that 4, right? So 4 squared is 16. So now you got 280 divided by 16, right? Let's approximate that 16 is a 14. So 280 divided by 14 would give us 20, right? So 20. So that's what that factor comes out to. Now we just got to handle the exponents of 10. Negative 11 times negative 10 to the negative 11th times 10 to the 24th. That's going to give you 10 to the, what's 24 minus 11? 13. There we go. And then you got 10 to the 13th times 10 to the 22nd. Well, that's going to give us 10 to the 35th. Yep. Now that's on top, but we're going to have to divide by this guy. So 10 to the 8th squared, that's going to be 10 to the 16th. So 35 minus 16 is going to give us 19, yeah? 19? Yeah, that's what's cooking. Okay, so basically we're going to get 20 times 10 to the 19th. So we should have 2. I'm approximating this bad boy as 2.0 times 10 to the 20th newtons. Okay, let's Google and see what the actual force is. It turns out that if you actually, yeah, don't worry about the math. This is like exponentiation math that you're going to have to get more comfortable with as you get into high school. Okay, so I knocked out a bunch of this for you really quickly because I wanted you to see that how this was done. But it turns out that the actual, like if you use 2 decimal places throughout, you get 1.97 times 10 to the 20th. Okay, newtons. And let me just draw that a little better. So you actually get to 1 decimal place, you actually get exactly 2.0 times 10 to the 20th newtons. So we got this right. Okay, we got this right. Okay, so I know that's a bunch of exponentiation math that you're not accustomed to, and this isn't a math class, so we're probably not going to spend a bunch of time going through a bunch of these questions at this level of detail. Okay, so don't get too concerned if it looks like I rushed through the math. All right, but this is correct, and this is how this formula is used. Okay, I wanted you to see that done. We may do some more examples like this. We may not. Okay, I'm going to pause and take questions. Last bit. Okay, last bit. So what about other gravitational forces? Okay, we will discuss those next time. Okay, next time. So that's all for today. We're going to go ahead and get these notes turned in. Yep.